Hello folks, welcome to Rational Science. And as I said in the description, I'm on the road, partly because I've got arthritis. I'm trying to see if I can do something about it, health issues. You have the Sandman, he puts little grains of sand in little kids' eyes every morning. Well, he does something different to me. He comes in with a baseball bat, beats the crap out of me, throughout the night. I wake up in the morning, with pain all over the body. Anyways, I got to lay off the booze and do a little more gym. If you do it the other way around, Mother Nature punishes you. Anyways, I'm not going to say much about extinction today, except that, it looks like we're in some kind of the beginnings of maybe World War III. Wars all over the place, okay? And not so much that that might lead to nukes, but it's got to have an effect on the global economy. And again, here we argue that it's going to be the economy that's going to fail us. Okay, so extinction might come around faster than you might think. Maybe some of you think it's maybe 20, 30 years or more down the road. It could happen even within the next 5 years for all we know, So keep that in mind, sleep with one eye open. Anyways, I hope everybody's can hear me okay. I would appreciate a confirmation, from anyone, okay, that you can hear me, okay? Okay, so let's begin. We're going to be doing a couple of things here today. We're going to be doing, once again, ether. There's a lot of loose ends. People need to be to brush up on some of the issues related to ether, and I think we haven't covered the whole subject. Okay, so hopefully we do a better job today of getting to the nitty-gritty. And then we have the subject matter today, which is this bending of light thingy. We're going to see if we can bend light for you today. Can you hear me? Okay, thank you. Appreciate it. Okay, so let's start with the first one. I'm going to do a little very quick review of what a couple of fellows out there, etherists, said, and then I'm going to address what they said. I'm going to answer them. I don't like to leave these things out in the open and letting people just think whatever they want. No, I want to get to the nitty-gritty, and some of these etherists, they don't understand the arguments. And so I reinforce it. If they come back, well, they'll listen and understand, hopefully, and that's all we can hope for. Okay, so here it is. Etherist the other day said, he says, I can use some kind of medium out of my mind, referring to the ether. He said, what will that serve? I don't know what ether looks like. It's all supposed to be invisible and intangible. Not being good at drawing stuff, and doesn't mean that it doesn't exist. Okay, so those were his main arguments. Okay, and so let's go through them real quickly here, how we address each one. First one, he says, you want me to draw you the ether? Yeah, I do. And he said, I can draw some ether like you drew me your ropes. Okay, good, that's what we want. There I drew a rope, you can see it there in front of your eyes. That's more or less what a rope looks like. Okay. And he says he can draw you some kind of medium out of my mind, just like you drew the ropes. Yeah, but see, he doesn't do it. He's not drawing the ether. He's not illustrating the ether, so we know or understand what he's talking about. We can visualize, see what he's talking about, right? If it's an object, if it's a thing. And he says that obsession of yours is ridiculous. What will that serve? And it serves at least two purposes. Okay, it determines whether you understand the fundamentals of physics. And you can show us what's going on through your mind when you say ether. Okay, so those are the main points that we want answered. We want to make sure that this fellow understands. He understands what he's talking about when he says ether. Not so much us, we want to understand as well, but it starts with him. He's the guy who's proposing ether. He's the fellow who's supposed to make sure that everybody out there understands what he means every time he pronounces the word ether. Is it an object? Is it a concept? Is it a thing? Is it an abstraction? What is the ether? So you can't use the ether until you clarify all that. You can't begin in the middle of your movie and say, I'm going to start moving the ether. I'm going to be doing fluids, the fluid flow, flowing fluids and the fluids that flow, flu flow, flea flow. No, you can't start in the middle of your discussion, your dissertation. You got to start at the beginning. You got to present the objects. That's how we do it in physics. Okay, so he continues. He says, I don't know what ether looks like. Okay, so he confesses there. He doesn't know what it looks like, so that's why he can't draw it, I guess. Any more than you know what your threads look like. Not true. I mean, there's a thread. I drew it for him. That's what a thread looks like. Just take any string, thread, wire, whatever. That's more or less what we're talking about. Some thin, elongated object. Period. That's it. Nothing out of this out of this world. Nothing out of the ordinary. It's all supposed to be invisible and intangible. Remember? And no, the word object. The definition of the word object is that which has shape. There's no provision for tangibility or invisibility. So it serves no purpose to really bring in tangibility and visibility into, when analyzing something such as the ether. We're not talking about touching or even seeing it. We're just saying if you're going to propose the ether as the medium that mediates gravity and light, no problem, but then show us this mediator, this mediator. Okay. Do you know what air looks like? Yeah, we do. And there you see I gave two examples. One is the air around the Earth. It looks like a ring in 2D. It looks like a shell in 3D. And there you had the astronaut pops a balloon. Some air comes out of there, right? We color-coded it so you could see it. Okay, so you know what we're talking about. And both those, the air and the air in the balloon and the air around the Earth, both have shape. In fact, everything that is made out of atoms had better have shape. Whether you can see it or not is irrelevant. The question is, does it have shape? It's a yes or no type of question. The question is not, what is the shape of a blob? Okay, I guess you could answer, it's blob shape. Okay, so whenever they say, what is the shape of? No, that's the wrong question. Does it have shape? Does energy have shape? Does field have shape? Does mass have shape? Does time have shape? That's the question. Does ether have shape? Well, the answer is no. Ether is a concept. That's why it doesn't have shape. That's why he can't draw it. He's trying to draw love. He's trying to draw intelligence, conscience. You can't draw those things, those words, those concepts. Okay. Okay. So he says not being good at drawing stuff doesn't mean that it doesn't exist. And he dismisses all this as word salad. It goes from one ear through to the next without anything stopping it in between. Okay, so to him these are just words because he doesn't pay attention. He thinks that doing definitions is known as word salad in his religion, I guess. Semantics, word wizardry, whatever. They don't do this. And that's the big problem with science today. They give you all these irrational explanations primarily because they use concepts as objects, meaning they haven't really defined their concepts as objects. In other words, they haven't identified any object. They haven't pointed and said tree, rock, house, and so on. They start using words as if you understood that they were objects. That's the way it's handled today. And that's a big problem because it's a problem of communication. Okay? You don't understand a physical interpretation because there is no physical. It's all abstract, it's all mass, it's all time, And so, if you're going to bend time and move the mass, what have you understood, And they get away with all that stuff in mathematical physics, but the dissidents are in no better shape. You get the electric universe, the etherists, the flat earthers, they do exactly the same thing. They don't realize. You have to start by defining your terms and pointing at the objects. Then you can start your presentation. No one does that. Everybody skips over those steps, says, well, you know what I'm talking about. No, we don't. Okay, so please be careful with your language, and point to the objects and define your concepts. That's the way it should work. Okay, so how did this fellow end this time around? He sent me a note there, and he put a comment, and he says, I was going to draw for you my ether, but nah, you would still find something negative to say. Why would I even bother? You're nuts. So, yeah, he ran away with his tail between his legs, and he got the boot. I mean, essentially he couldn't defend his religion, okay, his ether. And that happens with all etherists. I haven't seen a single etherist in the last few years that has come here that has been able to defend either the definition of ether or defend ether as an object, as a thing. They can't do either one because they don't have a definition. They just say it's a fluid. It flows. Flow. Okay, that's what they say. And what is that? I mean, I need to see what's flowing, what's fluing. Okay, fluiding. So these people don't do that. They just jump in the middle of the show and they start, acting. You lost the first frames of the film. You don't know what the guy's talking about. And so this is the problem. And everybody out there has this. Not only the establishment, mathematical establishment primarily, as well as dissidents. Okay, so they all make the same error. You have to identify the objects. You have to define your concept. Now, one fellow here, he says, ether would be like the seed of an apple. There is your object, a seed. Okay, like Johnny Appleseed there, plants the seed and all the trees grow. That's how they want it done. Well, what can I tell you? Maybe this guy is just BSing. Okay, that's all he's doing. Maybe he's not serious. Okay, but the reason I put that comment there, even if he was kidding, is that it reminded me of this. Let me show it to you first. What was this? 1999, and you have astronomy, how it all began. And you have Stephen Hawking, wrong one. Stephen Hawking and Neil Turok explain the universe's origin. Okay, and here I always keep these good ones. Says, let's see if I see it here. It says beginning and the end. Okay, the beginning and the end. So they're going to talk about the alpha and the omega. Beginning, Big Bang, obviously. Crunch is the big crunch at the end. I don't know. And then here, give peas a chance. Okay, that's what the article was about. And here, let me show you what these fellows said. Okay, here's the magazine. I put it up here. Okay, it involves these fellows: Neil Turok, Alan Guth, and Stephen Hawking. Okay, how it all began there. And they said that the singularity that was already there looks more or less like a P. Okay, they call it the P instanton. And there you see it, singularity, instanton, and open universe. Okay, that's more or less the starting point. And so, the question is, how did he get there? Did God put this P in there? Was he outside of the universe? And a lot of religious folk, William Lane Craig, one of them, he says, what you proved is God. Because what you're saying is that it all started at a singularity, and where did that come from? Well, obviously, the big man, right? So unless you can get rid of the big man, I can put him in there. I can say, yeah, God made the singularity. How are you going to deny it? I mean, God was there first, and he put the singularity. What's wrong with that? I mean, if these guys are going to come up with a singularity, the P instanton, and say that was there, well, who put it there? And what was outside of there? That's the issue. I mean, if the P contains time, space, and matter, what's around it? And of course, that's the same question as what is space-time expanding against? This dark energy that's pushing everything away. What is it pushing against? And they say it's an irrational question. It's not a scientific question. We have no way of proving it. And it just is. And they give you a whole bunch of runaround. But they never answer the question. What's outside of it? They can't tell you. Of course they can't, because they can't conceptualize what's outside if space is within the P. That's the big problem, the primary problem. Okay, so here it is. This is what they said in that magazine in astronomy. It says, the reporter asks, what does this new creation model look like? Good question. What does it look like? Draw it, illustrate it. Neil Turok. Well, it's small and round, but not perfectly rounded. It has little dimples. It looks like a pea. Okay? The universe comes out of one formula in a beautiful way. Oh, yeah, they love beauty. Great. This is the simplest way for starting the universe. The simplest way of starting the universe. So the reporter asks, how did he get there? Okay, Hawking says, it's meaningless to ask the question. There is no outside the P, no before the P. It just is an object implied by the very laws of physics. Okay, this is what the wording that they throw in your face. And so the reporter says, but what created those laws? And interrogator answers, we don't know how to create physics from nothing. And that's the only question they really needed to answer. How did the singularity come into being? And he just says it there. We don't know how to create physics from nothing. And that answers pretty much all the questions. You know, and again, when I use my universal movie tool to illustrate what Turek and Hawking are saying there, this is it. You have God, right? And he creates something from nothing. And they always take you to frame 2. And they say there was something. There was a singularity in there. Might look like a P, like a circle, like a ball. We don't care. There's something there. But there was nothing, you know, in frame number 1. So how did something come from nothing? With or without God? I mean, if you want to put God in there, put him in there. I don't care. You know, just tell me the mechanism. Okay? How do you create something from nothing? And that's the only question that anyone who talks about Big Bang or creationism has to answer. And they never do. I mean, even the people who are in favor of God, no problem. You want to put God in the picture? I personally have no problem. Okay? The question is, how did God come into being? Did he have a mother? Was he there forever? You know, did he come into being? I mean, you got to answer that question. And you can't say, I don't know, because you're the guy giving the presentation. You're the guy who's proposing God. You can't say, I don't know. Then when you know, you come and give your presentation. Well, I'll allow you to give your dissertation when you finish your whole theory, your entire theory, and tell us where everything came from. If you cannot tell us that, then thank you. Come again next time, okay? See, under the rope model, very simple. The thread has always been there. No one created the rope because or the thread, the single thread that underlies all matter, because you cannot convert space into matter or matter into space. So the universe, meaning all the matter in the universe, right, was always there, will always be there after we're gone as well. But, and it's just a little thread, that very thin thread that weaves all matter, and it's wet in space. In other words, we say in because I guess there's no other word to use there. It's space serves as backdrop. What is space? Nothing. What is nothing? The opposite of something. Nothing, that which doesn't have shape. Something is that which has shape. Period. We're done. But these people say, well, we don't know how the instanton got there. We don't know how God got in there, you know. No. Please tell us. When you're through with a mechanism that converts nothing into something, please come and give your presentation. That's the way it is. Okay. So what is this thingy called the ether, otherwise known as luminiferous ether? Well, it's in the Wikipedia we find this definition, okay, or description, right? Ether was the postulated medium, thing, object, okay, something, for the propagation of light. There was something there that allowed light to propagate, okay? Now, the question is, you know, for the propagation of light, are we saying that light propagates through something else, a different medium called the ether, or is the ether itself light, the vibration or whatever of the ether? That's an important question to answer. It was invoked to explain the ability of the apparently wave-based light to propagate through empty space, a vacuum, right? Something that waves should not be able to do. Okay? The assumption of a spatial plenum, space completely filled with matter, right? Or luminiferous ether, right? Space filled with matter, right? That's what ether is. Rather than a spatial vacuum, provided the theoretical medium that was required by wave theories of light. In other words, what they're saying in general terms is that space is separate, distinct from ether. Ether is within space. And for that matter, you know, then you would have to answer, well, what is space then? You know, and they made space made of particles, which is exactly what the ether is, because ether is what occupies or is within the walls of space. It's what fills space, so to speak. Like if space were a container that contains all the particles known as ether. Okay, so all that's got to be clarified. You got to start there. You got to show us what the universe looks like. You know, space, matter, ether, whatever you want to put in there. False vacuum, space-time, no problem. But you have to define it. You have to tell us what we're staring, what our starting point is. Okay, you can't just start in the middle of the road and say, well, you know what the ether is, you know what space-time is, you know what the false vacuum is, or what virtual particles are coming in from the vacuum. No, we don't understand that, because if virtual particles come in from the vacuum, make themselves real, you know, momentarily, and then go back, then that means space is made out of particles. And if space is not made out of particles, and space contains these particles, that means you got to answer what space is. Okay, so and so on down the line, you got to clarify all that. You can't move beyond that. And the Greeks did their best, but they didn't do very good. And no one has done any better since then in mathematical physics. The ether required the existence of an invisible and infinite what? Material with no interaction with physical objects. So we have a material that has no ability to touch intangible material. Okay, do we have that? That's what everybody thought the ether was. And so when these people say it's a fluid, well, they haven't answered anything. First, you got to spend 10 years on your ether, on defining what the ether is or pointing to it, whatever. Spend 10 years developing your ether. Then we'll listen to your theory. 5 seconds will do. But 10 years is what it takes for you to really develop your ether, not theory, your ether hypothesis, your assumption. We need your assumptions, your suppositions. Okay, that's what we need. Okay, and just so you can see what the ether has been through the ages. Okay, here it is. You have all these fellows from the Greeks all the way to really to the end of the 19th century there, and a little beyond, but even people today talk about the ether. Very few, relatively, out of the enthusiasts talk about the ether. But this is what it's always been, just a bunch of dots, lines, you can say, segmented lines, you know, little dots, and they're flowing in a given direction. Okay, that's what they show there. That's what's illustrated. That's what's in front of my eyes. Okay, and so all these, you could say particles, because I don't know how else to see them. They're all, the arrow just shows the direction in which they flow. So they have all this rain falling on the earth and the sun and etc. Okay, I don't know if it's all coming from one side, and that would be an important question. Why aren't these ether particles coming from the other side of the sun, for example, right? So, you know, direction is important here. You know, because it's easy to say, well, why do things fall to the floor? Well, because the ether pushes them. That's a problem, because the Chinaman on the other side of the earth, his spoon falls in the opposite direction to me, you know, and so also towards the center of the earth. That means the particles over there have to be flowing in the opposite direction. Okay? So, yeah, and the problem here is you cannot explain ether for light or for gravity. You know, you cannot explain it with particles. And that's what the ether has always been, a bunch of particles, and that's why the ether really has died, but really it hasn't, you know, because what is absolutely true, you know, is that the false vacuum of the quantum mechanics, space-time, which is a bunch of events known as points, right? All these are ether particles. All these are ether theories. They're all ether theories. Humans, until today, until we came along, have always talked about particles, discrete particles. And you cannot explain a single phenomenon, invisible or intangible, out there in the universe with discrete particles. That's the whole problem. So anyone who does particles, meaning ether, space-time, false vacuum, whatever you want to call it, all those people will never be able to answer the questions of what is gravity, what is light, what is electricity, what is magnetism, etc. So you have to get rid of the particle hypothesis, the discrete particle hypothesis. And that's partly the reason quantum turned the particle, the corpuscle, you know, the real ball, the you know, that Newton had in mind, they got rid of that. And today what do they accelerate? Quantities. Okay, they accelerate values, numbers followed by units. Okay, here are, if you look up the word ether, on Google images, this is what you'll find. Okay, see, you can see there, everybody thinks of the ether in the same way, and that's what they use to prop up their theories. Okay, this is the assumption that it's a bunch of particles flowing in a given direction. So when I tell these ether as they come here that ether is just a bunch of particles, they say, "Oh, Bill, you don't know what ether is. You're wrong. Blah blah blah." Okay, I'm wrong. No problem. I'll accept it. You tell me what the ether is, and they can't. They say, "Well, it's a fluid that flows." Okay, so here's the ether. Everybody wanted to know what the ether looks like. Here it is. Okay, I'll show it to you for the first time in your life. That's what the ether is. Bunch of particles. They vibrate, and the vibration makes those waves. That's what it's always been. That's what always people had always in mind when they talked about the ether, especially in the 19th century when they said waves. Thomas Young suggested, or really it was suggested since the days of Huygens and Robert Hooke, that light was a bunch of waves, right? But Thomas Young showed through the slit experiment, at least, that apparently light had some kind of wave nature. And then Fresnel and others, later on Faraday and Maxwell, they got into the wave nature of light. And they were always thinking of this. They were thinking of ether vibrating. And when Michelson and Morley came around in the 80s there, 1887 I think it was, well, they got rid of the ether. They said, we can't detect any difference in light. When they split light, they couldn't detect the difference in speed of light in one direction or the other when the Earth just went around the sun. And so that's when they concluded, hey, there can't be any ether, especially not an ether light. If you think of a sandbox, nothing moving, just sand there, just sitting there. That's one possibility. The other one is the grains are flowing. So either they flow or they stand still. And either way, you cannot explain anything you cannot explain light, specifically light. That's what we want to explain. And you cannot explain it with ether. And so the vibration of these particles or the standing still of the particles, it doesn't matter anyway, one way or the other, it's all garbage. Ether is garbage and has always been garbage to this day. And quantum mechanics relies on the ether. Still, it's a particle hypothesis, and that's what they show, that there's a bunch of particles there filling up space. They come into the real world as virtual particles and go back to form part of what? The ether. And this Nobel Prize said, he says the vacuum, the quantum vacuum, the one they use every day in mathematical physics, is an ether. But they don't call it that because it's taboo. Robert Laughlin. Okay, so here's a flow chart for all those etherists who want to challenge what I just said. And this is what we're going to ask you. So I'm putting the cards on the table. You can't accuse me. Says Bill, you're going to trash whatever I put in there. It doesn't matter. That's my job. Just like your job is to trash me, my job is to trash you. That's what the scientific discussion is all about. If you can't defend your posture, well, it's not that you lost. There's no losing or winning in science. It's just that you can't defend your posture. So you have no case. You're the guy who's supposed to present your case to the jury. The jury are your peers there. Where they're listening to you and they say, okay, what is this guy saying? What is your ether? What are you proposing? So you have to tell them. And this is what we're going to ask you. I'm going to lay it on the table for you to look at. This is the ether flow chart, okay? What I call the ether flow chart. Is the ether infinite or finite? You need to answer that question, okay? No matter what. Is it malleable or rigid? I mean, you can make it of a single piece or segmented, it doesn't matter. But if it's a single piece, you can say it's malleable or you can say it's rigid. You can say either one, no problem. But you have to defend these ideas, these proposals. And is it equal to space? Or is it contained within space? I mean, are ether and space synonyms? Right? Or is one contained within the other, meaning really the ether within space. Okay, and in that case, you got to tell us what space is like. Is it container? Does it have, does it stop somewhere? In which case, you got to tell me what continues. What encapsulates space? Draw it. That's the question. Draw it. Okay. Okay. So here, one fella out there, because a lot of these ethers say, well, it's a fluid that flows, flow. Okay, great. Okay, so it's a fluid flow. And here you can see the type of problems that these people have in making their presentations, their dissertation. Instead of going out there and telling us, spending 2 hours on their hypothesis and saying, look, this is what a fluid is, right? They start in the middle of the show, the middle of the movie, and they start telling you what the fluid does and things about the fluid. But they never start at fluid. What is a fluid? And you can see here how they make their presentations. Let me show you this. And this is more or less how ether is in general talk, and why it's irrational, because they skip over the important steps. We never get a handle on what they're talking about when they're already talking about the motion, what it does. Okay, here it is. To get all this fluid dynamics going, we start at the subatomic level that underlies molecular interactions. We average out the molecules by establishing the fluid as a continuous field. This continuum is then discretized spatially and temporally, whatever that will mean. Oh, great presentation, whatever that will mean. I mean, this is how the guy presented his case in a prominent site, okay? So, yeah, they say it's a field. Like if you knew what a field is, what is it, a football field or a poppy field? What is it? And then, they just begin talking about the fluid. And that's more or less what all these people do. They listen to stuff like this, and then they just say, I'm going to say the same thing about the ether. It's a fluid, and let me tell you what it does. No, I haven't yet understood what the fluid, what your ether is. I mean, even in this case, you can see they're talking about a fluid. What is a fluid? Made of molecules, which are made of atoms, right? So is your ether made of atoms, made of molecules? And more than likely, the guy's going to say, no, of course not. Okay, then you gotta tell me a lot more about the ether before you continue, because if you're going to talk about a fluid, I'm going to say, oh, so you're saying they're made out of molecules and atoms. And if you say no, then you haven't started in the on the right foot. you skipped some important step there. Okay, so that's what the point is here. Okay, and and so the issue for this fellow who talked about the fluid, right, is here. You can see it. We want to know what the black stuff is that gives shape or contrast or contour to each one of his molecules. He started talking about the molecules, the visible stuff, and he forgot about the invisible stuff, or the black stuff there that serves as contrast. That's what we want to identify. Is he talking about, are these particles or whatever, these molecules in water? Are they in air? Are they out there in space? You got to identify the medium first before you can continue. You got to tell me everything that I see in that field of view. And so this fellow just jumped directly into fluids. He said, let me tell you all I know about the fluid. I'm an expert in fluids. Yeah, you might be an expert in fluid, but you know nothing about backgrounds. First, we need or about science for that matter. You need to identify the background. I need to see an object and a background. When you put a background, I need to ask you the question, what is that stuff behind it? You can't avoid that. And you can say, well, I don't know. No, you're giving the presentation. You can't tell me, I don't know. You put it there in front of me. You got to tell me what it is. You can't say that part, I don't know. Let me tell you the visible stuff. That's the way all these people talk. That's how they give their presentations. Okay, so more or less here, fellow throws that same question essentially in my face, okay, which is correct, no problem, okay. He says, so according to you, the universe is finite. Absolutely not. There's no such thing as universe. Universe is a concept. Only objects can be finite, okay. So what's universe? Universe, the definition, matter and space. Two things there, really a thing and a nothing. Okay, so we have a thing and a nothing. We have two. We treat the nothing as a thing for the purposes of identifying the word universe. And so we're saying there's two things there, or two concepts. Okay, and so universe is a concept. You can't say the universe is this, the universe is big, it's small, it's infinite, because the universe is a concept. You either talk about matter, and you say that matter is either finite or countable. You know, if you're going to talk about atoms, you know, you can say there's a fixed number of atoms in the universe, no more and no less. Okay, and then you can talk about space and tell us what space is. In our here in rational science, space is that which doesn't have shape. That's what space is. That's a synonym of nothing, of vacuum. Okay? And yeah, the single thread is an object. There you see it. That's what we propose. And as you can see, it's finite. Okay, because it's a closed loop thread. Okay, and it underlies all matter. It's always been there. It will always be there when we're gone. So he says, oh, what's it into? What's outside the wall? And again, there is no outside the wall. You can say the outside the wall, I guess he's talking about the thread, is the black stuff. And the black stuff is not a stuff, it's nothing. It's the opposite of stuff. It's that which doesn't have shape. That's what the black stuff is. I put a square around it only so that to limit it, but you have to assume that this black stuff has no borders, no edges, no surface, okay? Because it's that which doesn't have shape. That's why we can't draw space. Okay, and the thread is within space, and it makes up every single atom, every single rope that interconnects every atom in the universe. And this is more or less the flow of thought. We have the single closed loop thread. Okay, you have to think of it as a rubber band, but that doesn't stretch. Remember, the thread does not stretch, and people sometimes ask that question. No, it's made of a single piece. It's malleable, and it's closed loop, and it doesn't stretch. Okay, I don't know what other thing you want to know about it, but just ask. It's very thin. How thin is it? In physics, we say it's very thin. That's as accurate as it gets. Okay, we don't care about numbers in physics. We don't care how big it is. We don't care how small it is. We don't care how thin it is. It's very thin. And it's very long if we were to undo every atom in the universe, and that's what we use. We use the adjective very, okay, or adverb in this case. Okay, it twines and turns into this rope-like entity, right? So that's what's going to make every rope that connects every atom, that connects every rope, that connects every atom in the universe. So we have atom, rope, atom, rope, atom, rope, all through the universe, and you can see there that every atom in the universe is interconnected. We're connected to an atom at the opposite side of the universe. Okay, that's why the Andromeda galaxy is being pulled towards Earth, and Earth is being pulled towards the Andromeda galaxy, because every atom in the Andromeda galaxy is bound to every atom on Earth, including every atom in your body. Okay, so that's the assumption, called supposition, assumption, hypothesis. Okay, so that's what we propose. And so with that, now we can explain, what light is, the torsion of the rope that you can see up there, the 2D, 3D rope that interconnects two atoms. The atoms pump, expand, and contract, known as quantum jump. And when they do, they torque the rope. And the torsion of the rope is light. And the reason we have gravity is that all these ropes, they don't tug, okay? They don't tug, but as two objects approach each other, the ropes fan out, and so you have acceleration of gravity. That's light and gravity in a nutshell there for you, okay? Okay, so that's the model, okay? So I don't know what the issue is, and here, just in case, we have a little evidence for those of you who want proof, evidence, etc., authority, tradition, democracy, all the people who voted for the theory. A lot of people are into that. In science, we don't pay any attention to that. Opinions have nothing to do with anything in science. Okay, but here we have evidence, proof for those who want it. Here's Richard Muller. He's at UC Berkeley, and he says, so for example, here, if you have the Earth, there's a big mass here, and you have you with your little mass here. He drew it there on the board. You can see it. Every atom on Earth is pulling on every atom of you. You're also pulling on it. Simple, straightforward. How do you pull on an atom on Earth? How does one of your atoms pull on an atom of Earth? And how does one atom of Earth pull on you unless there is some elongated entity that interconnects us? Intangible, invisible, elongated entity that connects the two atoms. If you can tell me that, hey, maybe you're going to win a Nobel Prize. There is no way of explaining that except that there is some invisible, intangible entity that connects every atom. Okay, and we made a pair of twine threads because we have torsion, and torsion is what light is. It's always been confused with this up and down transverse wave or standing wave or whatever. Okay, and what's been the problem? Well, the problem all these years, all these centuries has been that people have never been able to see or touch the mediators, okay? But you're supposed to make an assumption, like, they talk about entanglement. What is entanglement? One particle affects another, and there's no mediator. Entanglement means equal, right, or colon, right, followed by no mediator. That's what entanglement means. Okay, so every time you hear entanglement, it means no mediator. EPR, Einstein-Podolsky-Rosen, no mediator. That's what it means. So whenever they mention these fantastic scientific words, they mean no mediator. Action at a distance, which is the scientific term for black magic and witchcraft. Okay, that's what it is. Okay, so we have two things, two objects, two particles, whatever. And the question is, there's something happening in there that you can measure, but you can't see the mediator. Okay, so this one does something and affects this one, either instantaneously or after a while. It doesn't really matter. This one affects that one, but there's no mediator. You cannot see it or touch it. There's nothing there. Okay, so you make an assumption. Okay, you make an assumption, and whatever assumption you make, these people, the mathematicians, what they do, they put an equation to describe that. They describe what they think happened in there. Okay, and so let's say this one affects this one somehow. Again, through time, instantaneously, any way you want it, doesn't matter. This one affects that one. You can't see or touch what's in between. And so they put one in there, something in there. Okay, they forcefully put something in there with their imagination. They say, well, I think it's a bunch of invisible rabbits. They're jumping up and down, right? Maybe you found the wave nature of what's happening in there. You say, I think it's a bunch of rabbits that are just jumping up and down. Invisible, intangible rabbits, right, that are going from point A to point B, and that's how A affects B, okay? We can't see them. It's action at a distance, but really it's not really action at a distance. There is something there, and we're going to say it's a bunch of rabbits that are jumping. So this is what you visualize. Let me illustrate it for you here. This is what you visualize, okay? You see rabbits going from left to right, okay, on your screen. And you say, okay, and so now you go out there and you do your equations, you measure, and you come up with an equation, you win your Nobel Prize, you go on the talk circuit, right? Because you've discovered what was in there. It was a bunch of rabbits that were jumping, okay? It turns out that, Mother Nature put something else, something different in there that you didn't even think about. And it's this. So worm, that's torquing. So what you thought was jumping rabbits was a torquing worm. Okay, and it's a little different. The equations that you would need for that would be different. So you went out there and did all this work, okay, on jumping rabbits. You had all these discrete rabbits, and you put them in your equation. You describe them perfectly well, but it turns out Mother Nature doesn't have jumping rabbits. Mother Nature had, a torquing worm. And so the question is, the top one, the same thing as the bottom one there, I mean, if you make equations for the top one, turns out that Mother Nature has something different, has the bottom one. Have you wasted your time, 400 years of mathematical physics describing that which ain't, which are the rabbits out there, the discrete stuff, and not the elongated continuous worm that's at the bottom, that doesn't move anywhere, just torques in place? So it is important to identify, the mediator before you do any mathematics. Otherwise, you're wasting your time. And all these people are talking about particles and particles and particles. The etherists, the electric universes, everybody talks about mainstream. They all talk about particles. They all want to simulate everything with particles. The atom, 2 particles, a proton and an electron. Done deal. Then you say, is that your atom? Well, not really. We don't know what the atom looks like, but that's how they simulate it. And that's the one they're going to use for ionization, electricity, quantum jump. They do it all with this atom, the quantum jump, the electron jumps back and forth, around the proton, ionization, the electron leaves or falls, leaves, or another one comes in there. So they all do it with a planetary model. And when you say, is that your atom? Is the planetary model your atom? Well, not really. We don't know what the atom looks like. So you need to know what your atom looks like before you go out there and do all this stuff saying electricity is the flow of electron beams from atom to atom. You cannot say that until you tell me what your atom looks like. Otherwise, you're doing all this thinking, all this measurement, all these equations, and you don't know what you're measuring. What are you measuring? Are you measuring rabbits, jumping rabbits, or are you measuring a torquing worm? You need to determine that before you do a lot of math. And that's the problem with the etherists. They start telling you about the fluids, but they don't tell you what this fluid is. They don't draw it for you. They don't illustrate for you. Okay? And if you want to illustrate, you got to see the whole thing. Like, I want to ask you, what is a table? I don't know what a table is. Here's the Klingon. He asks, what is a table? And you point to a table. You don't have to be the best artist in the world. You can get a sketch of a table. You can get somebody else's picture and say, this is a table. And you point to it, and now he knows what a table is. Is a table made out of atoms? Yeah. Is it made out of molecules? Of course. A table is made out of all these things, but we don't say, well, a table is what it's made out of, because then an elephant is what it's made out of. A rock is what it's made out of. A tree is what it's made out of. Are we going to count the number of atoms? Say a tree has 5 billion atoms and a table or a house has, 6 billion? Is that the way we define table? Is that the way we define house? No, we point and say that's a house, that's a table, that's a tree, that's a rock. And that's what we want to do with the ether. Point to something that has shape, and then you can do whatever you want with it. But that's the starting point. You can't do that. You got nothing. You got to work a lot more on your hypothesis. Okay, so let's move on to the subject matter of today, and that's gravitational lensing. What the hell is gravitational lensing? I'm wondering. Well, it's the bending of light, essentially. That's what it is. But let's go with the formal definition, because I'm not going to put words in their mouth. I want them to put words in my mouth here, right? Okay, let them hear it from the horse's mouth. Okay, here it is. Here's the European Space Agency and NASA. This is what they have for gravitational lensing. It goes more or less like this. Gravitational lensing occurs, right? It's an occurrence. It's an event, phenomenon. When a massive celestial body, such as a galaxy cluster, causes a sufficient curvature of space-time for the path of light around it to be visibly bent, as if by a lens. The body causing the light to curve is accordingly called what? Gravitational lens. Okay? And I want to focus on that word path. Okay? Because this is going to be the key word here throughout the lecture today. Path can be an object, like a dirt road or a trail or a road, whatever, a highway. Or it can be a verb, the itinerary, the trajectory. And mathematical physics likes to confound words. They like to mix them and say it's a verb object, it's an object verb. In other words, they use the word path in both ways in the same sentence. And that's what I want you to focus on as I go through the lecture today, okay? Keep in mind the word path, okay? That's going to be the tricky one. It says, according to Einstein's general theory of relativity, time and space are fused together in a quantity known as space-time. Within this theory, massive objects cause space-time to curve, and gravity is simply the curvature of space-time. As light travels through space-time, the theory predicts, it's going to do some predictions here, that the path, taken by light will also be curved. What are we talking about? Path curved? Well, it looks like, are they talking about a road? Or are they talking about an itinerary? What's being curved? by an object's mass. They're going to curve the path. Okay, gravitational lensing is a dramatic and observable example of Einstein's theory in action. Extremely massive celestial bodies, such as galaxy clusters, cause spacetime to be significantly curved. And that's interesting because spacetime is a concept. It's four number lines, which they call coordinates or dimensions, depending on the day of the week. And they say these number lines are curved. That's great. So how do you curve a number line? Is a number line a thing that you can curve like a banana or a hammock? In other words, they act as gravitational lenses. When light from a distant light source passes by a gravitational lens, the path of the light, again, the path of the light is curved. Are we talking about an itinerary slash trajectory, motion, or are we talking about a road, trail, highway? What are we talking about here? What do you mean the path is curved? And a distorted image of the distant object, maybe a ring or a halo of light around the gravitational lens, can be observed. Okay? So that's, in a nutshell, the definition or the notion of what a gravitational lensing is. It's a phenomenon, okay, that they observe, the astronomers see out there, a little light around a halo, so to speak, galaxy behind a galaxy, a star behind a star, that sort of thing, okay? And here we have an illustration, okay? And let me turn this on. I think this is from the Wikipedia. So just watch. There's no sound here, but you can see what they're referring to when they talk about gravitational lensing. It's just an illustration of how light from a galaxy from behind shines around a galaxy that's in front of it. And so they say what's happening, light is curved by the mass of the galaxy that is between your eye and the faraway galaxy. So here it is, just an illustration, a little GIF here. You can see the background and the foreground galaxy there. And you can see what happens to light. You're going to curve it, okay, to your eye, to the detectors here on Earth. Okay, and that's essentially what it is. Okay, so it's just the curving of light. Okay, it's just the curving of light around a galaxy. It's a very simple concept. I don't think you need to know much more than that about this gravitational lensing. You have something behind another. You have an eclipse, right? You have a umbra, penumbra, whichever, one behind another. And you can see this thing, or the halo at least, through a galaxy that's in front of it, that is eclipsing it. Why? Because they say light curves. Okay? That's the explanation. That's the physical interpretation for why we see that. Okay? So they're explaining a phenomenon. They're giving you a physical interpretation. They later on, when you put them against the wall, they say, "Oh, we don't give physical interpretations. That's not part of our job description, mathematical physics." And so they dismiss all that stuff. Well, do you or don't you? Well, they do, because otherwise their equations are worthless. So they have to turn it into some kind of physical interpretation, some kind of explanation, some kind of mechanism, cause. Okay, they have to give you that, because otherwise their equations are worthless. Just that simple. Okay, so here we have it. Fellow everybody knows, his name is Matt O'Dowd. He works for people at PBS. Okay, and he gives you an idea of what this gravitational lensing is all about. Listen to him carefully. Okay, I'm gonna just mouth the words that he said. So I'm not putting words in his mouth in a way, but it's what he said. I just said it with my mouth. Okay, here goes. In the real universe, both space and time can be curved. The curvature produced by mass gives gravity. The path traveled by light follows the curve. And so gravity bends the path of light. Good old Matt O'Dowd, he is a caricature of a scientist. He's not a real scientist. He just parrots what the establishment, fed him. That's what it is. And so, what can I say? These are the people who talk on the internet There's tons of them. There's only little old me against all of them, so there's tons of them. And of course, they're going to give you the party line, that's all. But they cannot explain a single phenomenon. And they admit that they cannot explain a single phenomenon. Or as Richard Feynman said in the 60s, he said, physicists or mathematical physics has given up on that. They don't give physical interpretation. They give you an irrational one. When you call their bluff, they say, well, we don't do that anyway. It's not part of our job description. It's not our line of work. So why did you give me a physical interpretation if it's not in your line of work, if it's not part of your job description, your everyday duties? Okay? Why did you give me this BS interpretation? And I'll tell you why. If they don't give you a physical interpretation, their equations are worthless. That's why. And again, they could be doing equations for jumping rabbits, and maybe what they're looking at is a torquing snake. So that's another thing. Well, anyways, good old Matt, he mentions one of the first guys to prove, that Einstein was right regarding this. Light bending, okay? And this is the picture that is so famous out there in 1919. There you see one of the articles that came out in those days, okay? It says, lights all askew in the heavens. Men of science more or less agog over results of eclipse observations, okay? Einstein theory triumphs. That's when Einstein became a big man. He got his Nobel Prize 2 years later. Okay, partly because of this, right? He got it for the photoelectric effect of 1905 that he mathematized, you could say, and but he was also given it because of this, because his prediction came true and people were changing their minds about how the universe works. Okay, so it says there, stars not where they seem to be. Okay, yeah. And but nobody need worry. Yeah, okay. So anyways, the point here is that you can see the halo around the eclipse of the sun, and that halo is a star behind the sun. Okay? And so they said, hey, Einstein was right. Light does curve around, okay, around the sun. When there's an eclipse, you can see it there. You can see the glare of a star that's behind the sun. Okay, so this is what they showed, okay, that light curves around. In fact, the sun's light curves around the moon there. You can see it there as well. So I guess we're all, in agreement. Light seems to curve around the sun, right? And so keep in mind two words. One was path, okay, and the other question you need to compare is curved. We can put warp there, we can put bent there as well, versus deflected. Does light curve or is light deflected? Okay, keep that in mind. We're going to get back to that, okay? Okay, so here's my illustration of what Mr. Eddington had in mind. Okay, there's some kind of wall, okay? Maybe it's not on the outside, but it is in a way, because what they're saying is that the sun weighs down space-time, creating those walls in space-time, and the little photon or the wave, whichever, has no other choice but to slide around or drift or roll around those curved walls made by the sun. So you don't have to think of this as gravity pulling towards the center of the sun. You have to, which is what Newton suggested. You have to think of this as the sun weighing down space-time, warping the walls through which the photon has to slide. So the walls are on the outside, okay, not on the inside. Very important. And this is essentially what Einstein proposed, and this is what we have even to this day, that this is the explanation for why light curves. The sun weighs space-time downwards, and the photon has no other choice but to slide around in a curved space/space-time. Okay? Essentially, they're warping time, whatever that means. They're warping time. Okay? Okay, so here we have, because of these ideas, you have the first one here. We call them idiots. What's an idiot? Idiot's a person with big ideas. Okay, so we call them idiots because they don't have little ideas. They have idiots. We call them idiots. Okay, here's one of the conclusions from these idiots, and this comes out of the Wikipedia. It says that point particles can also curve space-time. I guess they should if they're point particles and they have, I guess, mass. That means every particle in the universe, keep this in mind, okay? Every particle in the universe is weighing down space-time somewhere. So space-time is not a smooth thing as they always show you, you know, this canvas is full of potholes. And I mean, not just one here and one there. I mean, all of space-time is just practically covered with potholes because every little thing weighs space-time downwards, I guess, downwards, whatever downwards is out there, you know. Okay, so everything, every little atom in the universe is weighing down space-time. That's the proposal by general relativity by Mr. Einstein. Okay, so they're saying it all weighs everything down. Okay, and so yeah, the point-like particle, right, assuming it's got some mass, I guess, weighs down space-time, and that means light never should travel straight, you know, or rectilinearly. It has to go through all these little potholes every step it takes. You wonder how poor old light does this. I mean, not even God designed such a monstrous world. You know, this is just beyond our imagination. But that's what they say. A point particle, what is it? Lacks spatial extension. Okay, so there's nothing there. It weighs something. That nothing weighs something, meaning it weighs down space-time, and by doing so, it deflects the path of light. Every step light takes, it's deflected. You try to explain that, okay? So light never travels in a straight line in general relativity. It can't because all masses weigh down space-time, every atom. Okay, so here we have another group of idiots, big ideas, right? Here it is, and they say that because of this, right? Does light travel straight or curved? Well, let alone light, even the Earth, they say. In 4D, the Earth orbits around the Sun in a straight line. In a straight line. In 4D space, the projection of a straight line onto a 3D volume is still a straight line, but it may have some oscillations due to the presence of a fourth spatial dimension. So there you have the rational orbit that normal people, even people in the ancient days, knew about. You know, they were aware that the Earth goes around the Sun. And these people say, no, you're wrong, Bill. Our relativity gurus tell us something different, that the Earth and the Moon travel straight, and I guess they go outside the solar system. I mean, I don't know what they mean by straight. Okay? But they say that in 4D they travel straight. And since everybody says that we do live or exist in a 4D space-time here, I guess the one on the left is out of bounds. You know, it's wrong. You know, the Moon and the Earth travel straight. Now you know it. You heard it here first. Okay, so we have all these people, you know, they have all these irrational conclusions, all these irrational explanations, physical interpretations, mechanism, causes. They have all are irrational. The words coming out of their mouths are all irrational. Okay, the way they express themselves. Maybe they just need to better their language. No problem. But then work on the language. Don't tell me that the Earth travels straight in 4D space-time, but it curves here on Earth. What the hell does that mean? What can it possibly mean? Okay, and the same with light. Light, Earth, doesn't matter. Okay, gravitational lensing is essentially the same experiment or observation out there in space as the experiment here on Earth known as the slit experiment. You know, here you have straight light, and it curves around the Sun because space-time is warped by the presence of the Sun, right? And so, yeah, you get this curvature of light according to general relativity. And that's more or less what happens in the quantum world with a slit experiment. You know, the light goes straight, but somehow on the other side of the slits, you have all these waves. They curve around, they begin to interfere with each other. So you go from straight light to curved light. So all these people see in curves. They say everything is curves. And, we do have an explanation for the slit experiment, which more or less has a little to do, it's going to be the same mechanism we proposed for gravitational lensing. So here's the illustration of our mechanism of how the rope explains this. And what it is that, you have essentially a light source, and all the ropes are connected already to everything else. And so if you put not a pair of slits, you put, some kind of needle, something like that, okay? You put something like that in front of it, and the question is, if you have photons, little particles, they should go straight out. They have nothing to bounce against and come back in. And that's the way mathematicians illustrate the slit experiment. It hits the walls of the slit and then bounce inwards. But if you have no walls of slits, if you only have something in the center, how do you produce the coming back in of that whole beam? What's it bouncing against? Why does it come back in? Okay? And in this case, why does it produce these waves, these transfers or whichever waves they want? I mean, it doesn't matter. They can produce longitudinal transverse waves. It doesn't matter. But how does it come in? Why don't they just continue going straight if there's nothing to bounce against to come in, back in? There's no sill, no window sill, in other words, right? Where to bounce against. Okay, and so here's my needle experiment. And what I did was I put a laser pointer. You can do this at home, very cheap experiment. Not $1 billion experiment. You put a laser pointer, and you put farther down, a few meters down the road, you put a chair with your cork and a needle stuck to the cork. Okay? And you're going to shine the laser pointer exactly at the needle. You got to, position it there so that it hits the needle. And on the fore wall, you will see fringes, which is what Thomas Young saw for the first time. In fact, apparently Newton was the first one to carry out that experiment according to Thomas Young. He says that in his book, okay? But here it is. I carried out this experiment some years back. I think it's still valid, so here it goes. Watch it carefully. Here you can see the laser pointer, okay? And then another chair, I put a needle stuck to a cork, okay? And then farther down the road, you can see some light out there. So I'm going to go to that light now. Okay, you can see what the light does, what it is. All static, so nothing's moving. And you can see the fringes there. Okay? Okay, very straightforward. You can do this at home. Prove it to yourself. Okay? You don't have to believe my word. Okay? So the question is, you can produce fringes with a needle. You don't need slits. You don't need two slits. And then if you don't have the slits, you don't have anything for light to bounce against and come back in. If you need the bouncing without the slits, without the window sills, right, the frames, it'll just go straight. It should go straight. There's no reason for it to come back in. But it does. But as you can see with a needle, it curves around the needle. And so that's like the case of gravitational lensing. Are we saying that the needle is weighing down space-time and that's why it curves light around with, needle, how much does it weigh? 1 gram? And it curves light around because of all that weight? Or like the other guy said there, point particle also weighs down space-time, it bends space-time. That's why light curves inwards, because you're bending space-time around the needle. You see the issue? Okay, those are questions for you to ponder. Okay. So what's the big problem? Well, why do we have this problem with gravitational lensing and the slit experiment and all these other good things? Entanglement, you can also include in there, etc. Language. What's called word salad, semantics, what these people dismiss as, oh, you're doing a semantic argument, Bill. Yeah, we're doing a semantic argument. No, the guys doing semantic are the other people, not me. I'm trying to define my words. I'm accused of doing semantics. No, it's the people who use the words wrong who are doing semantics and word salad and word wizardry. Okay, so here it is. This is the problem. What is a mathematical physicist? An individual who doesn't understand the difference between an adverb and an adjective. Okay? Here are the verbs, common verbs that mathemagicians, typically confuse for nouns. Itinerary, it's not a noun, not in physics. Orbit, orbital, motion, trajectory, path, energy, charge, number, mass, force, field, time. None of these are nouns in physics. In physics, it's got to be an object to be a noun, okay? That's the only one that can serve as the subject of a sentence. Those are the only nouns allowed in physics, okay? It's not the orbit of Jupiter, it's Jupiter orbits. Orbits is what it does. And then you have ether, wave, plasma, electricity, singularity. You know, what is a singularity? Space-time, black hole, dark matter, function, conscience, and tesseract. These are just some of the words. I could go on with more. These just came out of the top of my head. Okay, what's an adjective? A qualifier or modifier of a noun or of an object in physics. Here we're talking about an adjective for the purposes of physics. Okay, we're saying that what qualifies a physical object. That's what we're talking about. It's what is, right? Not what it does. And there you see, straight, curved, bent, finite, infinite, continuous, bound, flat, warped, perpendicular, segmented, inert, exists, 2D and 3D. You know, if something is three-dimensional, that's adjective of an object. On the other hand, we have adverbs. Those are qualifiers of verbs, motions, and concepts. Primarily concepts, we say, but we put those in there so that you know what we're talking about. It's about what it's doing, not what it is, but what it's doing. And it refers to motion primarily. And there you can see some of the adverbs, which are treated as adjectives or who knows what, or sometimes not used at all. Deflected, diverted, swerved, incessant, ceaseless, perpetual, constant, curvilinear, rectilinear, dead, alive, living, being, and 4D. Four-dimensional, what is that? Means time. Time had better involved motion, and hopefully a 4D entity is something already in motion. You cannot say, well, I cannot imagine a four-dimensional space-time like Mr. Hawking said. No, of course he cannot, because he's talking about motion, he's talking about a concept, he's talking about a dynamic concept, and he's trying to imagine a physical object. So this is where we start. We start with language. We have a problem with the language that these people use today. And we're going to see some of the problems that these confusions that these people have, or misinterpretations, what they cause in physics. Okay, they cause enormous problems in communication, and it's them who are doing word salad because they're treating all these words in an irrational manner. Okay, it's not wrong, it's irrational. Okay. Okay, so what is light? Here we have it. Okay, we have straight transverse electromagnetic wave. That's what we thought a wave was, at least all the way till Maxwell, right? And now we're starting to curve light around. You know, I don't know how many beers these guys drink, but they curve light around. Okay, they say it curves around the sun. So are they warping the wave? I mean, don't we need to know if it's a wave or a particle for that matter, right? Here's a wave, and you're bending it, you're warping it, you're turning it around, you're curving it, okay? And so the question here is, are we going to say that a wave is curved or that it is deflected? Are we talking about something in motion which is taken out of its itinerary? I won't use the word path because it's very confusing. Are we taking it out of its trajectory? Is that what it is, which means it's deflected? Or are we talking about a physical object that is curved like a banana, like a hammock or whatever? Are we talking about a continuous object here for the wave? Is that what a wave is? Okay, does the wave of light stretch from here to Andromeda uninterruptedly? Or does it flow like a little boat from Andromeda down here? You know, little wave that moves little by little, you know, all the way down here. So we need to establish that. Are we talking about, is the wave interrupted at some point? Is there a beginning to the wave and end to the wave? You know, outside the atoms, I mean, because if it has a beginning in an atom over there and it stretches or extends uninterruptedly all the way to my eye, then yeah, the wave connects my eye to that atom. Okay, do we understand that? Okay. Otherwise, it travels like a little boat, like a sailboat. You know, a little wave just emitted, and ciao, you're good riddance. You're out. So you got to determine whether the wave is continuous all the way to Andromeda Galaxy, extending all the way down there, or if it travels the wave. They always give you a piece of a wave, several links. I'd like to know if the wave stretches uninterruptedly from Andromeda to my eye. Okay, and this is the other version. This is the particle version. Okay, straight line again. They really are referring to rectilinear travel, not a straight line, but they turn these verbs and adverbs into adjectives and nouns. That's the problem. Okay? I mean, are we talking about straight line or rectilinear trajectory, rectilinear itinerary? What are we talking about? Are we talking about all these particles moving? Is that what it is? Or are we talking about a straight line? See, that's not a line. That's a bunch of dots. And if each one is location, one of the two, either there's one dot that is occupying all those locations, or there are all those dots occupying each one its own location. And I guess they all move forward or something. So you got to determine what you mean by straight line of photon, which is what the term they use. And then you have the bent line, which is a curvilinear or curved line, they call it, right? Or a warped line. So again, are we talking about a line, or are we talking about a whole bunch of apples? Okay, if a whole bunch of apples, you got also to explain, why, what causes it to bend like that, to warp like that. And they say, well, because space-time is bent or warped by the sun, and then the photon has no alternative but to slide or roll along warped space-time. That's the explanation we receive. Okay, if that's the case, then space-time has to be a physical object. You cannot later say, well, we don't know what space-time is, or space-time is not an object, it's a mathematical concept, because you're warping a thing to give me a physical interpretation. So you cannot later deny what you just said. Okay, otherwise these people live in contradiction, or they give you what they always say, well, we don't do that, that's philosophy, that's interpretation, we don't do that, we do equations. If you do equations, stick to equations, don't try to bluff, don't try to don't try to convince me that you understand how this universe works, that space-time is warped and you've proven it with so many experiments. No, you got to make sense of that. If you can't make sense of it, then don't give me any physical interpretation. Just stick to your equations and stick them up your nose holes also, because they have no importance in physics. In physics, we don't use equations. In physics, we have to explain the mechanism. Okay, that's what people want to know. People want to know why this spoon, falls to the floor. That's all you need to explain. You tell me what causes that to go to the floor and not to the ceiling. Then we're done. But don't tell me that space-time is warped and space-time is, you treat it like a physical object, then deny and say, well, we don't understand it anyways, it's not part of physics anyways, and then why did you do that? Why did you try to convince me that space-time is warped? Okay. Because otherwise your equations are worthless. That's why. Yeah. Okay, so here we have Mr. O'Dowd again, put him up there. So again, so he says, and so gravity bends the path of light, and the path traveled by light follows the curve. Okay? So he concludes that, yeah, gravity bends light. Okay, but again, you got to explain it. He's just describing that, and that's his interpretation, that's his opinion, but he has no justification for what he's saying. Right? So yeah, he's a caricature of a scientist. He's not a scientist. Scientist is someone who can tell you why. Okay, and if he's going to say that this is caused by warped space-time because that sun weighs, space-time downwards, then he's treating space-time as a physical object. He cannot later deny it and say, well, I was just only kidding. I was giving you an analogy, and you're not supposed to take it literally and all that good stuff that mathematicians, the arguments they created over the years. Because that's what they do. They give you one to show you that they know and that you don't. They're going to educate you, and then you say, well, yeah, but space-time is a physical object. Well, you weren't supposed to take it literally. It's not a trampoline. It's not a canvas for real. It's the way we explain our mathematics, bring it down to your peasant level. The question is, who's the peasant here? Is it the listener or the guy giving the dissertation? Okay? And then here we have our conclusions. We can say, here it is, questions to ask a mathematician. Okay, these are conclusions. Is light a flow of particles? Or is it strung out waves? They extend forever, the waves, or do the waves travel as a little sailboat, meaning they're discrete waves, meaning it's a wave packet? What is a wave? Does wave get broken at some point? Is it cut off from other waves? That's one of the questions you need to answer. And then you need to know what a particle is. Is it a value? Is it a magnitude, an amount? Is it a number followed by a unit? Is that what a particle is? Or is it a corpuscle? Is it a ball? We're going to talk about balls, or are we going to talk about, values, mathematics? Okay, that's important. Are we talking physics or are we talking math? Okay, and they never do that. They want to put both of them together, call it mathphyz, mathematical physics, right? And again, is light a wave or is it but if you look at the wave, it's a bunch of vectors, magnitude and direction, that's a number. So is a wave just a bunch of numbers, a magnitude with direction? What is this? What is a wave? Okay, it's a description, mathematical description of something. And they represent it with this, vectors. And they move the vectors around. They show you this wave in front of you. You say, okay, I understand it's a physical object, right? Because I see something in front of me that's got shape, it's moving. No, what you're staring at is a mathematical concept that they're moving. Bunch of vectors, okay? Magnitude and direction, perpendicular to each other. How do numbers go perpendicular to each other? How do numbers have direction? How do numbers flow? Okay, so we need to establish what light is. Is it a wave? Is it a particle? What do you mean by particle? What do you mean by wave? That has to be up front. If you can't begin that, you cannot enter physics. You cannot begin your dissertation in physics. These people jump in the middle of the show and say, well, you know what a wave is. It's that thing that's moving there on the screen. No, I don't understand what I'm looking at. I'm looking at a bunch of vectors that are moving, numbers that are moving. Woo, woo, woo. How much did you drink today? Bartender, I want what he had. Okay, and then we have, does light stretch uninterruptedly from Andromeda to Earth? If you're talking about particles, you can say, well, the particles travel. So they're all discrete, so they're not connected to each other. Why would they travel in a straight line or in any way for that matter? That's one issue on the one hand. But if they're waves, the question is, does that wave stretch all the way to your eye? Wave, no interruption? Or is there a sailboat, a little wave packet that just travels, through the air, through space or whatever? You got to determine that. Okay, so, and then is the meteor of light made of a single piece or is it made of parts? Are we talking about particles or are we talking about single piece, meaning, if the wave is made out of a single piece? This wave, whatever the wave really is, okay? Does light bend, warp, curve, or does it deflect? If you're talking about photons, what do you mean you're bending a photon? What do you mean you warped light? What do you mean you warped or bend or curved light? Are you saying you curved the photon? Or are you saying you deflected the photons with warp space-time? Okay, so they're not clear about that. They use adjectives and they use them to give a physical interpretation in which they're talking about adverbs, okay? Physical, in physics, not in ordinary speech, okay? Adjectives qualify nouns. So if you're going to say curved, warped, bent, they're talking about a physical, the table can be bent, okay, or broken or warped or whatever. That's different than saying that a whole bunch of photons are traveling in a curved manner. No, they're traveling curvilinearly, rectilinearly. They're deflected. You can use any term you want, but make sure you use the right terms. That's why it's an issue of language. And these people are saying, oh, light is warped. What do you mean light is warped? What is light? Is light a single solid thing that you warp? Or are we talking about the deflection of photons? That has to be clarified. The language is absolutely essential to understand what these idiots are saying. Okay? If so, what was it that bent, right? Those are the questions you got to ask these people. Don't ask me these questions because I don't do mathphyz, So whoever does mathphyz has to defend his position. I defend something else. Okay, so here we have it. Illustration of that. Here goes. You can see, are we saying that the wave travels like a little sailboat, or does it extend all the way to Earth? Okay, that's the question. If it extends and it continues, you know, otherwise you got to tell me where the wave begins, where it stops. Okay, you see that? So it either travels or it extends. One more time there. Okay, so you need to know the beginning and ending of a wave. Okay, so yeah, these are the things that people have to, these are the questions, the structural questions, the assumptions, the hypothesis that people have to question. And mathematical physics doesn't have any, because they don't have definitions and they don't have objects. They deal with concepts which they converted or morphed or reified into concrete things, into objects, and they treat them as objects, you know, field, mass, energy, etc. They treat them as physical objects, and then they apply adjectives to what in front of us is patently a verb. So they should be applying adverbs, and they don't. They apply adjectives because an adjective goes well with a physical interpretation. Adverbs talk about motion. So they don't say that something is incessant. They say it's unbounded. They don't say that, or they use the word path, which is ambiguous. You can say, what do you mean by path? Well, I mean that it could be, you know, a road, a highway, or it could be the itinerary of you on that road, on that highway. So if the highway is curved, you curve. No, I don't curve. My itinerary is curvilinear, not curved. What's curved is the highway. And so you have to distinguish between warped, curved, and bent on the one hand, which are adjectives for objects, and itineraries, which, or trajectories, which can be deflected or incessant or perpetual. They have other qualifiers which are known as adverbs in physics. You have to determine if you're talking about an object or a verb. You know, and once you determine that, you got to use an adjective for these and adverbs for that. That's how it is. Okay, that's physics. Okay, so how do we do it under the rope model? Here it is. The rope extends all the way to Earth. Okay, and then with this we can explain. And here it's only one atom on each side. Okay, we have gazillions of them. But here again, one rope only, and you can see why the moon doesn't fly away, because it's every atom in the moon is tied to every atom on Earth. And that's why you can see the moon at all times. You're seeing through these ropes. It's the torsion going in both directions. And then you see the difference between quantum and the rope model. One is just discrete particles, and the other one is interconnected ropes. One more time here, you see the rope, one rope only here. You can see different frequencies there. Okay, the moon going around the Earth also, because every rope connects every atom on the moon to every atom on Earth. And there's the difference between quantum mechanics and what we propose. Okay, straightforward. Okay. Okay, and so here, just in case for those of you who have doubts, more proof, more evidence. Those of you who want evidence proof, you know, here it is. We have Mr. Richard Milner, and he says, what? Every atom on Earth is connected to every atom of you. You are also connected to it. Let's repeat that. Let's see if you can get that in your head. Every atom on Earth is connected to every atom of you. Every atom of you is connected to every atom on Earth. That's what Muller is saying, professor at UC Berkeley. Okay? Now, what part of that did you not understand? It's straightforward. Let's repeat it one more time, all at the same time now. Every atom of you is connected to every atom of Earth. Every atom of Earth is connected to every atom of you. How else can you explain that unless there is a physical connector which you cannot see or touch? Okay? And you say, see, touch? Yeah, because an object, a thing, is not that which you can see or touch. It's that which has shape. This connector, this mediator, this agent that we put in between atoms has shape, but it cannot be seen or touched.